For the last section of Chapter 11, we are revisiting similar shapes, this time in 3 dimensions. We certainly have done quite a few similar shapes this year. All of these guys were in the Similar Shapes lecture. They are all similar. They are all the same shape with proportional sizes. The same thing is true of 3-dimensional shapes. They are also similar as long as they have the same shape with proportional sizes. The official definition says similar solids have the same shape and all of their corresponding dimensions are proportional. Here I have a pair of rectangular prisms that have had their dimensions labeled, so I need to build out an extended proportion. Find a pair of corresponding sides, like the 20 and the 15, then find another pair, like the 12 and the 9. Finally, match up the 32 and the 24. Since all of these ratios reduce down to the same thing, 4/3, we know that these are similar solids. If I was going to check if cylinders were similar, all I need to do is check 2 things, the radius and the height. Those are the only 2 dimensions for a cylinder. The examples so far have been easy to match up the dimensions because they've been oriented the same way. But what happens if you have something like this, where it isn't as obvious which corresponds with which? In cases like this, you always simply match up smallest to smallest, which in this case would be 30 and 28. Then match up the 2 medium values, 31 and 29. And finally the 2 largest values, 32 and 30. Even with screwy orientation, if you put smallest to smallest, medium to medium, and largest to largest, you should match up the corresponding pieces correctly. Here the fractions do not reduce down to the same thing, so we know for sure that these are not similar solids. Now we get to the piece which is just adding on to what we already know. We already did most of this in section 10.4. In fact, this is the exact slide from section 10.4. All we are going to do now is add one extra piece to it. Can you guess what we will be adding in? What seems to be missing considering what we have been doing all chapter long? We are just adding in a line about volume. That's it. It works logically just the same as we did before. Volume is units cubed, so the ratio we use is a cubed to b cubed. That's it. Now a quick example. You are given the base areas of 2 similar pentagonal prisms and are asked to find the volume of the larger pentagonal prism. This is a very typical problem for this section. You should always start off with the same 2 steps. Reduce the given information. It will make your life infinitely easier. Use those wicked mad calculator skills of yours and find that in this case the numbers reduce down to 25/64. The next thing to do is to fill in the chart. Some of you will find this an unnecessary step, but it really helps in doing these types of problems. You will be far less likely to use the wrong information then. Here I have 25/64, but which box does it go in? Well, we were given dimensions for the base areas. Areas are units squared, so it should go in the a squared to b squared spot. Now take the square root of that to get 5 to 8 for a to b. Now we need to cube 5 and cube 8 to get 125 and 512 for a cubed to b cubed. With these 2 automatic steps filled in, the rest of the problem is pretty easy. We are asked to find the volume. So you need to ask yourself, which of these 3 ratios in the chart will we use for volume? We should be using 125 to 512. So that starts off our final proportion. 125 over 512 equals something. Well, we were given the value of 11,000 centimeters cubed for the smaller pentagonal prism. So that 11,000 should go with the smaller number, the 125. Now just cross multiply and solve for x. You should get a value of 45,056 centimeters cubed for the volume of our larger pentagonal prism.